All right, so I looked over the assignment that I had you complete by yesterday, kind of a recap of the end of Module 2 and the start of Module 3, moving from what we had been talking about with distance formula and absolute value at the tail end of Mod 2, and then moving into our expressions with function notation and what we began last week. So on Thursday. Looked pretty good. I didn't see any major issues, like questions that everybody missed. I'm sure some of it took you a little bit, like maybe a couple tries on some of them. But in any case, it looked very good in general. So just coming up, a couple of reminders. Next week, Thursday, is our first test. So by probably later this afternoon, maybe this evening, depends on how stuff goes. By later this afternoon, I should have up some test review material for you. Just kind of a bunch of practice questions related to a little bit of everything, some of which we haven't quite talked about yet because the test is in a week and a half. But I'll have up a bunch of questions. The test is going to be multiple choice. So in terms of like what, like how to write out your work and stuff, that's not really pertinent. What you're going to need to be thinking about in terms of how to answer this, as you've seen a lot of the questions in iMath, it's like a select all of the above that are true, or things like that. It's going to be similar sorts of, you have to read carefully to make sure that you're interpreting the statements correctly. It's not computation heavy. There's not a lot of calculatory questions. It's more about how do I write an expression that represents the change in the volume of this box when the side length changes, from those sorts of things. Like how do you represent something, pick which of the expressions does the following. So don't worry about like what kind of calculator do I need to have. I'll take a look again, but you probably don't even need to have a calculator. I'll double check the test before I say that for sure, but it's not computation heavy. It's mostly about writing expressions correctly, interpreting expressions correctly, putting things together and figuring out what combination of things needs to happen. There's maybe a couple of division questions, so I'm thinking like, maybe you want to have a calculator just for dividing, but it's nothing super high tech. So where we left off on Thursday last week, we were talking about the first half of this sheet, which this was posted in Canvas, right by the link to YouTube. We talked about distance that a car traveled, and we were using some function notation. D was the name of the output variable that we compute using the function W with input variable T. So W of T, when I do W to input T, it turns into D, if you want to think of it that way. So W is just like a randomly selected letter because I'm tired of using F all the time. But distance was a function of time, and we answered a bunch of questions related to what these various expressions using function notation mean or might mean. And then I asked you to look over the questions about the sync, the second page of this worksheet, over the weekend, and I want to talk about those now, just to make sure we're still on track with understanding how to use and interpret function notation, because it's very useful to be able to express a relationship without needing to do the computations immediately, both just if you want to discuss what it is without having to figure it out, but also thinking about things you might be using this for. A lot of computer programming sorts of things involve thinking about how do I express this relationship generally, not in one specific case with specific numbers, but what do I need to do, what relationships used, and some of these have numbers that I'm putting in, but we don't have a formula. Well, for the previous one, we didn't have a formula at all. It was just a generic W of T. The second question, there's actually a constant rate of change relationship. So in this one, we're going to actually write the function rule that relates the height of the water in the sink and how much time has gone by. So in this, the way it's explained here, it says that after time t minutes, we have a function w, capital W of t in this case, that gives us h, the height of the water in the sink. So the input again is time and the output is height this time. And our function is also called w, it's a capital W. But in any case, if I want to write an expression for the change in the height of the water in the sink between time 2 and time 6 minutes, using function notation. Now I have this information here about like how fast the water is draining, but question 1a isn't asking us to compute anything. We just want to write an expression or use function notation to represent this amount of change. So the change in the height of the water. We have a formula that represents, or we have a function notation that represents the height of the water. So if I want to represent a change in the height of the water, that's like a final minus initial sort of situation. Any thoughts on what I could write for part 1a? What expression? Any? Maybe? Yeah.
Maybe W in parentheses minus W in parentheses 2.
Okay, yeah, so W in parentheses, what's in the first set of parentheses that you said?
6.
Yeah, W of 6, oops, 6. So W of 6 represents what here? What's the meaning of the expression W of 6? Anyone?
The height sink after 6 minutes.
Yeah, the height of the water in the sink after 6 minutes. And then W of 2 is the height after 2 minutes. So this is the height at a later time minus the height at an earlier time. Now, based on the story that's going on here, is the answer to this, would the result numerically from this be a positive or a negative number?
Negative.
Yeah, it'd be negative. Does that make sense in this question to get a negative result for something like this, a change in the height of the water in the sink?
No,
So for the change in the height of the water in the sink between time 2 and time 6, is it okay for that to be negative?
yeah.
Yeah. What does it mean that it's negative?
The water is decreased.
Yeah, the water's decreased. So if I said that the change in the height of the water was, let me just say a number, like 4.2 inches, if I just said that without a story to go along with it, like, oh, the water changed by 4.2 inches, you'd probably imagine, okay, so there's more water. Would I say it's negative something, whatever it might be? If I said it was negative 4.2 inches, you know, like, oh, so the change is negative. That must mean there's something that's getting smaller, decreasing, going down. So even without knowing exactly what's going on, if you see that a change is negative, that's allowed. But having a sign, a positive or a negative, tells you what sort of change is happening. So it's very easy to forget about that when you've got a change that's positive, just because we don't write a positive sign in front of it, so you're not really thinking about what type of change it is. But when you see that negative, it stands out like, oh, this means something. Keep in mind that changes can be positive or negative. A positive number, you won't see a plus sign in front of it, but would mean increase or more, generally speaking. Sometimes it could be to the east or west or, some sort of direction that isn't necessarily automatically assumed to be positive, but would be defined in the particular problem. But when you see a negative, that kind of stands out like, oh, wait, what's the negative mean? So in this case, it'd be the depth of the water in the sink, or the height of the water in the sink, is decreasing over those 4 minutes. So let me ask this. Is this the same as, let me not ask that. Let's take a look at the next question. The reason I don't want to ask it is because the answer isn't really useful here. So using the constant rate of change given, constant rate of change was height decreasing by 1.23 centimeters per minute. So using that, how could I get the answer to part A, like a numerical result? It seems kind of weird. Like, well, because I don't know what W of 6 is, and I don't know what W of 2 is. However, in this case, it doesn't actually matter those are times that are 4 minutes apart. And since my water is decreasing in height at a constant rate, it doesn't really matter which 4 minutes those are, right? It could be time, as long as it's within reason, like it wouldn't be time negative something before I started draining the sink. Probably not time 4,000, the sink isn't that huge. We're gonna talk about issues of domain in just a minute. But over 4 minutes, any 4 minutes during the process of the sink draining here, the water would decrease in height the same amount. How do you find that amount? What's the constant rate?
1.25 centimeters per minute.
Yeah, 1.23 centimeters per minute. So 1.23 centimeters per minute for 4 minutes, any 4 minutes, is going to be, 4.92 centimeters. Now, this is decrease. So thinking mentally, okay, it's negative 1.23 centimeters per minute. But if I'm writing this in a sentence, I could say the water decreased in height by 4.92 centimeters. But I'm getting that from doing 4 times 1.23 centimeters. I said in those 4 minutes, be in any 4 minute time period, it would do the same. But if I wanted to write the value of the expression, W of 6 minus W of 2, remember we said that would be something negative, right? Because it was higher at time 2. The height of the water in the sink was higher at time 2 than it was at time 6. So if I wanted just a value for that expression, I'd probably be writing, like, what do we say that was? Let's see, 4.92. So the value of the expression would be something negative. If I wrote it in a sentence, I might not use a negative sign. I might use the words that say what the negative sign means instead. So I might say, all right, the value of that expression is negative 4.92, meaning the water height decreased. That takes the place of the negative sign by 4 times 1.23, or by 4.92 centimeters in those 4 minutes. And in fact, since it's constant rate of change, it'd be in any 4 minutes. So if you remember, I said earlier, like, we don't know the value of W of 6. We don't know the value of W of 2 in question 1 or in question 2. Now, if I told you for question, or A or B, I suppose, if I told you for part C, suppose that W of 2 is 8. First of all, what is the meaning W of 2 equals 8 with regard to water in the sink? What would that mean?
There's 8 centimeters of water left after 10 minutes.
There's 8 centimeters of water in the sink, so the height of the water, like from the bottom of the sink up to the top of the water, is 8 centimeters at time 2 minutes after we started trying to drain the semi-clogged sink. So if I know that, and then I wanted to know W of 6, what's the height of the water after 6 minutes have gone by, and I know what the height of the water was after 2 minutes, well, now I can find not just how much it's decreased, but I can find what the new total is, right? I didn't have any like starting points to work from before. Now I do. I have a value for W of 2, not starting point as in time 0. I don't need to know what the height was at time 0. I could find it if I wanted to. But if I know that the height at time 2 is 8, and that the water's decreasing by 1.23 centimeters per minute, the water height is decreasing by 1.23 centimeters per minute. If I want to find W of 6, some later time, I take this starting time height and add on the change. The change is negative, so it's going to look like subtraction. But that means in order to answer this question, I could say, well, in function notation, I could write W of 6, well, what do I do to get that? I start with W of 2, and then I subtract,
4.92.
yeah, my 4.92. I'm going to write it out as 4 times 1.23, or 1.23 times 4. Let me put it in that way, that order. That way the negative's kind of closer to the 1.23. Obviously, those are the same. All right, so I have a starting point, and then I subtract some because the water's decreasing. Or, so I have this final value, later height is equal to an earlier height plus whatever change happened. The change happens to be negative, the sink's draining. But now I have a way to compute this since I know values. I could say that, what, W of 6 is 8 minus 4.92, 1.23 times 4, and whatever that comes out to be, a little bit more than 3, all right, 3.08, and that would be centimeters. And I could do that for any value. Starting from any point in time, I can find a later height, or I can find an earlier height, add that 1.23 centimeters per minute back on. Now, this isn't a question that I asked on this worksheet, but it's pertinent to what we're going to be doing next today, so I'm going to ask it right now. There's only a certain set of values of time that would make any sense in this question, right? Like time before 0, before I started draining the sink, I'm not going to be worrying about that 1.23 centimeters per minute. And I can't do this forever because the sink is only so deep, right? So suppose that I'm using this information here. Suppose that W of 2 is 8. Think about this for a minute. What's the largest value of t that would make sense to use in this problem if that's true? If W of 2 is 8, what's the largest value of t that would make any sense in this question? Or in other words, when does the sink finish draining? Because after that, we're not going to worry about how high the water is anymore. So take a minute, maybe do a computation. Or think about what computation needs to do. If you don't have a calculator, that's fine. Thought? Yeah.
How are we supposed to know if we don't know the height of the sink?
So the height that we're concerned with is how high the water is in the sink. So if we're given this, without this piece of information, we can't answer the question. But if I say that at time 2, there's 8 inches of water in the sink, and it's draining, then that 8 is the only height. I don't need to know how much taller it was to start. But you're right, without being given something like this, there's no way to answer this question. Without knowing an amount of water at some point in time, some sort of like matching pair of numbers, without that we can't answer this question. But oops, t equals 0 through So any thoughts about what's the largest value of t that would make sense to use in this question if I know the draining rate and this fact that W of 2 is 8? Thoughts?
T equals 6 maybe.
3 point,
I think T equals 6 maybe might be the largest. Because like if
t
we
equals
subtract-
6? So how did you get that?
Maybe I think like if we subtract 4.92 from 3.08, the answer would go in negative.
Okay.
And that means that there is no water in the sink.
Right, so 4.92 is how much the water shrank in 4 minutes. So I can tell that past times 6, another 4 minutes
Yeah.
wouldn't work because we'd be at negative height. So we don't want to run into negative height, essentially. So we can start from this 8. We also have W of 6 equals 3.08. We could also start from that. But if you can imagine, like just thinking about whole numbers, let's see. At time 2, I have height 8. At time 6, I have height 3.08. So at time 7, it would be 1.23 less than that. That's okay. At time 8, it would be another 1.23. That should still be like 2 point something less than that. Time 9 might be getting into negative territory. So somewhere between 8 and 9. What I'm really wanting to do is figure out when does W of t equal 0? Because if W of t is 0, the height of the water in the sink is 0, that means that the water's all drained. And it's not going to become negative. That doesn't make any sense. So I want to figure out when does W of t equal 0. For what value of t? Well, I don't actually have a formula written out for W of t. I could write one, or I could kind of think my way into an answer from this given information. But let's see, let's think about what if I wanted to write a formula for W of t, the height at any point in time, using, as I said, supposing that this is true, this W of 2 equals 8. Let's stick with that. So if I want to write an expression for the height in general, this y final, at any point in time, I want to know when it's 0. If I think W of t, y final, some mystery time t, I just need to know a starting height and how much it changes from there. Well, we did this sort of computation for a specific number here to figure out the height by time 6. If I want to find out the height by time t, mystery time t, well, I just have to have my starting point. I can use the same starting point, W of 2, and I'll write it with numbers in a minute, minus 1.23 centimeters per minute past this. So when I was using time 6, there was a 4 here, because that's 4 minutes after the time that this was the height, the time that 8 was the height. So more numbers version, W of t equals 8 minus 1.23 times something. I don't want a period, I just wanted more spaces. So this is the idea of point slope format, something, writing an equation. I have a starting point. It's not times 0, but it has some starting point to work from. I have a height of 8 then, and I want to know how many minutes past that point in time I've gone. Well, time 8, or height 8 was at time 2. So however far I am past time 2, that's how many minutes I'm going to use. That's where like the 4 came from when we're looking at time 6. If I changed this previous question to not time 6, but something about time 7, well, time 7 compared to W of 2 equals 8, that's 5 minutes gone by. Or time 10, that's 8 minutes gone by. Probably too much. But in general, oops, trying to release, there we go. My height is going to be based on, well, starting from 8. 8 is just an easy place to start because they gave me that information. I could work backwards and figure out what the height was at time 0, but I don't need to. That's actually kind of built into this problem. 2 minutes and 1.23, that's how much height we lost in the first 2 minutes before time 2, when the height was 8. But here's an expression. for how to calculate the height at any point in time. So if I want to know, again, this question I was asking, the values of t that make sense for this problem, we're looking for, well, we start at time 0 because we're not going to start using t values before we started draining the sink. And then we go until the sink is empty. Well, when's the sink empty? When does w of t, when does this equal 0? And it's not going to be a nice round number, but kind of estimating wise, we figured out it was somewhere between 8 and 9 minutes. So if we look at this expression, we can figure out, using some algebra, when does 8 minus 1.23 times t minus 2 equal 0? So solve for t, distribute, subtract, divide, general linear equation solving sorts of things. And I don't know what the number answer is off the top of my head, but I believe it's somewhere between 8 and 9. So somewhere between 8 and 9, or the solution to this expression, however you want to write that, is going to be the answer that we want. You can also see that just without even distributing, this would be the same as this, right? Setting equals 0, I can just move that whole chunk across the equal sign. There we go. 8 equals 1.23 times t minus 2. Or t minus 2 would be equal to 8 over 1.23 without distributing. So 8 over 1.23, add 2 minutes back onto that, and that's our answer, whatever that is. Here, out of curiosity, 8 over 1.23, and then add 2. So about 8.5 minutes. So what that is, I'm going to say about 8.5 minutes, or 8.5 is that largest value of t. We're slightly past that, but the sink probably is a little bit of an angle, so we'll just say 8.5 minutes. In terms of reasonable domain for this, domain being what values of the input variable make sense to substitute in, or in other contexts, it's what are you allowed to substitute in. I think we talked about that a little bit, like we don't have any square roots or logarithms or denominators or things algebraically to worry about. All we have to worry about in this case, in terms of how this function is set up, it's a linear formula, are what makes sense relative to the fact that it's a sink that's draining and at some point it's going to be done. So times 0 through about 8.5. You could write out an algebra expression to not have to round that off. But division by something like 1.23, chances are it's not going to come out to a whole number. So in any case, our domain here is 0 through about 8.5 minutes. Notation-wise, if I wanted to write that without having a sentence, I could write this as interval notation. And in terms of the domains we're worried about here, don't worry about parentheses versus brackets for something like this. We're just kind of estimating. 0 is certainly okay though, but 0 through 8.5 would be our values of t that we're using. And this is, again, it's not a coordinate pair, this is an interval. T equals 0 through t equals 8.5 is what this means. So that would be a reasonable domain for this, or logical or sensible domain to use. You'll see sometimes in other questions with parentheses, the difference between these is very slight. Sometimes it's extremely important when we're talking about practical domain and story problems. Lots of times it's like, don't really care. But the difference between these is whether it's the or equal to versus the strictly less than sort of inequalities. So t between 0 and 8.5 is talking about a range of numbers. Is it allowed to be 0? Is it allowed to be exactly 8.5? That's the difference between parentheses and brackets, where the brackets, the nice square ones, mean up to and including the endpoints. So t can equal 0, t can equal 8.5, and t can equal anything in between, whole numbers or otherwise. The one with parentheses would mean t can equal anything between 0 and 8.5, but isn't allowed to equal those values at the endpoints, which in this case, we actually know that it's fine. It's fine for t to be 0. It's fine for it to be 8.5 exactly. In fact, it was like up to 8.501 or something like that. So it's okay to be 8.5. But so we'd want to use the brackets one on this one. In a lot of cases though, and in many questions on the assignments you'll run across, either parentheses or brackets will be accepted because it's just kind of up to your interpretation of the question. That's not generally the biggest deal, and I'm not going to be quizzing you on should this be parentheses or brackets on like a whole bunch of application questions. That's not really the emphasis. I just want you to think about what numbers are generally the range of numbers that we like to use, or the interval of numbers. So, I don't want to get into the other question. I want to move on to other topics. So I just wanted to talk about, in this, what we talked about, some function notation, interval notation, the concept of a domain, but also constant rate of change. This constant rate of change, how you find the proportional changes when 4 minutes have gone by and we've got a constant rate of change situation. It actually doesn't matter which 4 minutes it was. So if I asked you to find something like how much the water decreased between time 1.7 and 5.7. Well, W of 5.7 minus W of 1.7 would be the exact same result as what we had before because it's this constant draining rate of the water. So that was also 4 minutes. So it's also 4 times 1.23 as the decrease in the height, or 4 times negative 1.23 is the change in the height during any 4 minute period. If you want to find a final value of y, though, or write an expression for the height, you have to have a value of the height at some point to start with, some sort of, like it kind of links it someplace, so that I have not just how fast something's changing, but I have to know how much it is. So just kind of like if I said, I was driving 45 miles an hour down the highway, where was I after 3 hours? Like, well, where were you? I have to give you some sort of location information for the amount of change to tell you something about my location. But you could talk about change, like in 3 hours, you know I drove, what did I say, 45 miles an hour? Must have been traffic. 135 miles someplace, just don't know where those 135 miles were. But if I give you a starting point, you can give me a finishing point. All right, so other things I want to talk about then. More in general, domain and range sorts of things. So I'm going to look at, let's see, this is the page. So this is Module 3, Investigation 2, as you can see here. So this is in the textbook section as opposed to the homework section. Let me make this a little bit bigger. And we talked about domain quite a bit. There's also something called range, which is the corresponding set of values for the output variable, the thing that you're computing something about, or in the previous case, the height of the water in the sink. So if you want to define a function thoroughly, we want to talk about the formula that relates something, what computation you do to relate an input variable and an output variable, or an input concept that I can measure and an output concept that I can measure. I need a function rule for that, but I also need to say, if I want to define it thoroughly, what is my domain and range? So what set of values am I using for the input values or for the input quantity? What set of values that is going to happen for the output quantity? Now, lots of times the range part is left off because if you have a formula and a set of input values, you can figure out the range from that. It's not easy. Finding the range of a function from a function rule is not always easy. It depends on how messy the rule is. Sometimes it's just as simple as with a linear function. if you know the starting value and the end value, and you have the formula for it, like, oh, well, it's going up the whole time, it goes from here to there, you can just use the endpoints, because those would be the highest and the lowest y values. The range values, graphically speaking, are about the vertical set of values that we have, whereas the domain, the input is usually graphed horizontally. It's talking about left to right, where does this graph go? And for functions, you can always connect left through right across whatever domain you have. But the range could go, you know, it doesn't have to just be a straight line increasing from left to right or decreasing from left to right. It could go up and back down. There could be weird stuff going on in the middle, like vertical asymptotes, all sorts of stuff, which would be holes in the domain, but nonetheless, that gives a weird range. So domain is about the independent quantity or the input quantity, the thing you get to pick, generally speaking, which is why it's called independent. Range is the dependent quantity. Range depends on what formula you're using, what your function is, and how that rule assigns values. So all right, let's see. I just wanted to go over that. Let's see. There was something, I thought there was something about intercepts on here. Oh, it's on the next page. Sorry, I'm just skipping ahead. I just wanted to go over, see those definitions. All right, here's the other definitions. And these are in practical use. A lot of times these intercepts, vertical or horizontal intercepts, have a lot to do with the domain and range. In lots of practical applications, we're stuck in the first quadrant because the values can't be negative, or maybe we're stuck in the fourth quadrant. The values have to be negative, but the input has to be positive. It just kind of depends, but you're often stuck in a quadrant. If you're stuck in a quadrant, your boundaries are often the axes of the graph. So those intercepts just indicate a place where the graph runs into one of the x or y axes, a vertical or horizontal axis. So because they're not always x and y as the variables, that's why it's referred to as a horizontal intercept and a vertical intercept. But those mean the same thing as if you are more comfortable with the terms like x-intercept and y-intercept. Same thing. It's just to be more general about it, because we don't have to be using x and y. We could use whatever letters we want. But those intercepts represent points where we're on one of the axes. So graphing stuff-wise, that means there's some sort of zero involved. If we're on the vertical axis someplace, at a vertical intercept then, y-intercept, y-axis, that means that our x value, input value, whatever it might be, is 0, right? Other way around, if I'm on a graph on the x-axis or the horizontal axis someplace, if I'm at a horizontal intercept, then I know that my y value or my vertical value, whatever that dependent quantity is, that one must be 0. So in the case of the sink that we were just doing, we had a height that started someplace at time 0, didn't really know what it was. By time 2, we were at height 8, it says 30 here, but just graphically, and it would have gone down until we reached the axis, right? And then after that, we don't care. We don't want to go down into negative y values because that'd be negative height of water in the sink. Doesn't make any sense. But what we actually found in that, by finding that whatever is approximately 8.5, if I were graphing that, that would be the time at which the height of the water was 0, the time at which the output was 0. So we would have had, just ignore what those values are, we'll start someplace up here and then go down to 0 on the x-axis and then stop. Because past that, it doesn't, we could keep drawing a line, but it doesn't make any sense relative to the sink. So these horizontal and vertical intercepts a lot of time have to do with practical domain, because they trap us in a specific quadrant where our values have, some specific sorts of, our quantities have some specific sort of value. It has to be positive, has to be negative, something like that. And once you cross an intercept, something has changed sign-wise that maybe no longer makes sense in the problem. So, well, as long as there's this question here, h of x equals 39 minus 6.5x represents the distance in meters that a tortoise is ahead of a hare in terms of number of seconds since the start of a 100-meter race. Now, I would say don't worry about trying to graph this, but if you want to read this question, it's kind of like the sink. This distance is 39 minus 6.5x, where x is the number of seconds that have gone by. So it starts at 39 and is decreasing by 6.5 meters. Is that what we're measuring in? Meters, yeah. Decreasing by 6.5 meters per second past that beginning point in time. Now in our sink question, we had not at time 0. At time 0, x equals 0. This would be 39. In our sink question, we didn't have a time 0. We had a time 2 and a height of 8 at that point in time. So it's a more messy formula than this. But this one shows us our vertical intercept, or our y-intercept. It's kind of in mx plus b form. Why I say kind of is the b's first. In practical applications, lots of times it makes more sense if you're reading a sentence. We start at 39 and then we go down by 6.5 per second. So that's why it's written in that order. But say, oh, start at 39, boom, that's here. And then I'm going to decrease this distance. It's not going down, it's not water in the sink, it's distance between the two animals. Decrease that by 6.5 meters per second. So eventually that distance is going to hit 0. If I want to know when, just like with the water in the sink, I want to know when is this equal to 0? When does 39 minus 6.5x come out to be 0? Or in other words, when does 6.5x equal 39? Well, 39 divided by 6.5, right? And there's no like plus 2 like we had in the last question, because it's just an x. But whatever 39 over 6.5 is, 6, that's when this equals 0. So what does that mean about the tortoise and the hare in 6? What is 6? 6 is a value of what, time or distance? 6, time, right? It's an x. It's x equals 6. X is an amount of time. So after 6 seconds, this expression computes out to 0. After 6 seconds, the distance between them is 0 meters. So after 6 seconds, one's caught the other. I forget which one it was. Distance that the tortoise is ahead of the hare. So the hare's catching up because this is getting smaller. So at times 6.5 seconds, the hare has caught the tortoise, or in any case, they're in the same location relative to the starting line. So in terms of domain for using this function, if I was just concerned about graphing this until the tortoise catches the hare, I'd want to graph this from time 0 to time 6. If I go past time 6, that's when the hare is in front of the tortoise, and I think the hare got lazy at that point in time and stopped running quite so fast. But in any case, that would be a point at time 6. Graphically, that would be on the x-axis, because at time 6, the distance is 0, the output is 0, so that's 6, 0 on a graph. Horizontal intercepts, also called x-intercepts, also called roots, sometimes solutions to equations, same thing if you graph them. Those are places where the output or the dependent quantity has a value of 0. All right, so we'll get into a lot of other solving and whatnot later, but I had one other thing I want to talk about today, and that is different module. So I hope that those concepts seem like something that you probably talked about before. I just want to make sure we're okay with like possibly slightly different terminology, horizontal intercept instead of always x-intercept, etc. But the one other thing I want to talk about is function notation stuff, composition of functions, and this is in module 3, it's part 4, I believe. Yep. Whew. And there's a lot of stories in here, but there we go. So here, where was this? All right, this is what I want. So we're just going to go through this kind of quickly. But this question 2 says, draw a diagram of a square and label the side length as x. We're going to measure the side length in inches. And then think about how, depending on how large x is, it would make our perimeter larger or smaller. All right? So, square if the side length is x, what's an expression that would compute the perimeter? 4x, right? So let's say, as it says in B, define a function g that inputs the square's perimeter and outputs the square's side length. So if I know that the perimeter can be computed using the formula 4x, so that's useful if you know the side length and you want to find the perimeter. What if I wanted the reverse? What if I know the perimeter? How do I find the side length? What's a formula that does that?
P over 4.
Yeah, p over 4, right? If we have a formula that we need, but it's not the form that we want, we can always rearrange it. If p is 4x, then x is p over 4, right? So this formula, p over 4, takes an input of perimeter and gives us an output of side length. So for this part B, if I wanted to define a function g that inputs the square's perimeter and outputs the side length, this is our function rule. That's the formula for the function. Now, if I want to write it as function g, and I say the rule is p over 4, what letter do I put inside the parentheses? G of what? What's the input to this function? Is it p or is it x? Yeah, p. I'm putting in p, right? Now what I get out is called x. So x equals g of p. If I wanted to say that, I could. G of p, though, when I have a formula and the variable in that formula that I want to plug in is given, when I'm writing function notation, that variable that I'm plugging in should be inside the parentheses. So if I want to write a formula for this number, whatever it was, part B, input is p and the output is the side length, I can say x equals g of p. The formula for g of p is p over 4. So I plug in a perimeter and I get out this, which I'm saying, all right, what is that? Oh, that's x. X is a function of perimeter. Side length is a function of perimeter. So if I want to know how does the square's side length change if the perimeter goes from 6 inches to 20 inches, I could compute that, right? I could also just write an expression with this. If the side length goes from 6 to 20 inches, or the perimeter, goes from 6 to 20 inches, then that's 6 and 20 as values of p. I could write out, well, between 6 and 20 inches, how much does it change? I want final minus initial. X final, I'm using x because it's that side length, minus x initial is what I want. So that's between perimeters of 6 and 20. If I change the perimeter from 6 to 20, how much does the side length change? Initial is 6, final is 20. And I could find the side length in either of those. All right, I just do p divided by 4. 6 divided by 4 and 20 divided by 4. Oops, no, equals. All right, I could find those answers, but I could also just write it in function notation, g of 20 minus g of 6. Final minus initial. So, one last thing, and then I've got some stuff for you to do. Define a function h that inputs the square's side length and outputs the square's area. So what if I have so the side length is still x. How do I use the side length in a formula to find area for a square? What would I do with x? X squared, right? So if I have a function h that takes an input of side length to give me the area, then h must do x squared, right? Area is h of x. So the thing is, I've got two functions that involve some of the same symbols. They both involve x, right? Function g takes perimeter and turns it into x. Function h takes x and turns it into area. So I can take a perimeter, turn it into a side length, and take a side length and turn it into area, which I could do those in sequence. If I said, well, suppose I've got a square with a perimeter of 6. What's its area? If it was just phrased as a question like that, you're like, oh, well, if I have a perimeter of 6, then I want to find the area. First, I find the side length, divide by 4, and then I square it. So divide by 4, and then square it. But that's just function g followed by function h. Right? We're just doing those in sequence. Take the result of function g, and then do function h to it. Find the area from it. Doing those steps in sequence is called a composition of functions. Sometimes it makes sense, sometimes it doesn't, to stick two functions together, because in order to chain two functions together or do one after the other, the output of one has to match up with whatever the input of the other is, right? So like if these both had like if it was area, h of x equals x squared, and the other one was perimeter, p of x equals 4x. The output of one is not the input of the other. You wouldn't stick them together like that. But if I have two that kind of coordinate like this, where I have the input to function g was perimeter, put it into my function machine, it turns it into side length. Oh, but I can take a side length, put that into function h, and it cranks out through its function machinery the area, squares it. So there's a notation for that, which we can use, and it's more succinct than what's written here, just quickly to write this. Let's see. I'd rather type this, but I don't have a blank. So if I had function g takes a perimeter and gives me a side length, x. Function h takes a side length and gives me an area. That means that I can chain together these. Take function g of any perimeter. I know the result from this is going to be a side length. So if I use that as an input to function h, do h of whatever g of p is. For any value of p, I can get a value of g, or get a value of that function, and then put that into function h to get a value of that. So this is h of g of p, meaning, well, it's just doing two things in a row, but we could simplify the process. Instead of having two separate formulas, if you're going to do this over and over and over again, Well, divide by 4 and then square. So if you can see this, f of perimeter length is area, which is side length squared. F of perimeter length over 4. So side length is the same as the perimeter over 4 and square it. So I could put these both together and call it called it a second function f, but it's perimeter divided by 4 and then square it. Turn a perimeter into side length and then turn a side length into area. And so we could come up with a general process to do that for any perimeter length, and that's what this is. This is a composite function. It is two things. It has two operations there, divide by 4 and square in that order, which is turn a perimeter into side length and then find the area that corresponds to that side length. But this is basic function composition, which we can do either just with formulas or in graphs. I just want you to take a look at this graph really quick, and we're going to talk about what this means. Now, if I can get this big enough to read it. Following graphs show two functions, f and g. Function g takes as its input the high temperature in degrees and outputs expected attendance at a neighborhood carnival, which that's the graph on the left. So here's function g. When it's cold out, not very many people come. The warmer it gets, the more people go to the festival. This only goes up through 75. It doesn't go through Arizona temperatures. So we would expect maybe if it was Arizona temperatures, that would go back down past a certain point. But up through 75, yeah, okay, it's nice out. Maybe it's winter in Arizona. So if it's up to 75 degrees, there's more people showing up. Now, the more people show up to the carnival, the more money they make because they charge admission. So function f takes as its input expected attendance at the festival and has as an output expected revenue in dollars. Now, if they're charging everybody the same amount, this isn't going to be weird and curved. This is just going to be, another person comes, we get more money. Another person comes, get more money. And the same amount per person, or constant rate of change. You can see this linear function going with revenue. So if you can see the relationship between this and the square perimeter and area question earlier, these two things are related. They involve some of the same quantities. The first thing we're measuring is what temperature is it, tells us how many people will come. If I know how many people come, then I know how much money I'm going to make running the carnival. So I should be able to stick those together and say, well, based on what temperature it is, how much money am I going to make? And just do it in one step instead of two. So, for instance, just to pick something where I can kind of see this, let's say it is, what's a number that's maybe easy to pick here? This. Halfway between 15 and, let's say about here. Looks like if it's 20 degrees, there's going to be 100 people come to the festival. This is halfway between 15 and 30, no, let's see, 15 to 30, maybe that's like, what are we counting in here? 57 and a halves? So maybe this is about 25 degrees. At 25 degrees, looks like about 100 people will come to the fair. Well, and if 100 people come to the fair, looks like my revenue is a little bit under $300. So if I wanted to graph something, and there's a blank graph down below if you pull this up on your own computer. If it is, what did I say, about 25 degrees, I know there's going to be about 100 people. And if there's 100 people, that corresponds to a little under $300. I'm just going to say $300 to make it easier to use nice round numbers. And this is revenue. So we say, okay, if it's 25 degrees, we get $300. Well, if this is function g over here, g is what turns the 25 degrees into 100 people. And function f is what turns the 100 people into $300. So I could say this is f of g of 25, or I could pause differently, f of g of 25 corresponds to this point in a function composition graph. If I were going to graph this, I'd need to label these, but I'd have an input of 25 people, or 25 degrees, sorry, and an output of $300. So I just did two things to get from 25 to 300 there. And we could go through and pick that out for a lot of things. Like, all right, so what about if it is 75 degrees? 75 degrees looks like there's 650 people, right? So 75 degrees gives me about 650 people. And if there's 650 people, let's see, looks like about somewhere between 1,500 and 1,800. I'll say 1,650. In revenue. So 75 degrees gives us 650 people, gives us about 1,650 in revenue. Just estimating. Kind of hard to see what all of these numbers are, but just as an estimate, if I were going to graph, again, the composition of this, f of g of x, it would have a point input 75 degrees, output $1,650. And the 650 is just kind of, it's in the middle someplace. It's not part of either the output of f, so we wouldn't graph it horizontally, and it's also not the input to g, so we wouldn't graph it, or it's not the output to f, so it wouldn't be graphed vertically. It's not the input to g, it wouldn't be graphed horizontally. The 650 wouldn't appear in the graph. It's a computation that gets us through. So we use that to get from one graph to the other. All right, so in any case, what I did want to have you look at for today, and we've got about 15 minutes left here. So let me refresh this. Should be available now. Yep. You should see, if you go into your rational reasoning, there's a quiz 3.1 through 3.5. It covers things about domain and range and just using function notation and constant rate of change that we talked about before. Has a little bit with function composition thrown in there also. This is due by midnight tonight. There is no, you're not going to be able to see when you enter your answers whether they're right or wrong. You're not going to get the score till after you're done. You can work on the question, then change your mind and go back and enter it again, and as many times as you want through midnight. There's no deduction if you changed your mind because it didn't show you whether you were right or wrong. But you can start on it now if you would like, with classmates around and us around to give you some kind of input and pointers. If you have questions, it is 8 questions long, if I remember correctly. But they have multiple parts to them, as most of the homework does. I don't think it'll take you more than, once you start working on it, 45 minutes to an hour. You can start it, stop it, go back as many times as you want. That's not a timed thing. It's just due by midnight. That's the only timed aspect of it. There's no password. This isn't proctored and it's going to lock you out of looking for stuff. This is I want you to try it, but I want you to take your time and think about it and give your best efforts into getting these correct. So, take some time. Tutoring is fine if you go to online tutoring or otherwise. This isn't a lockdown, you should have this all memorized sort of quiz. It's just kind of a more, I want to see what you know by today, and I want to know how accurately you can figure these out in a relatively short period of time, being whatever we've got, 16 hours until it's due. But it's not like a multi-hour assignment. So if you do have a computer, you can even do this on your phone. iMath is set up to be able to do most of this stuff at least easily on a phone. Graphing is probably a little bit harder, but there isn't graphs to make, just graphs to read in this one. But take a look. You can work with other people if you want. You can work on your own if you want. This is all up to you. But this is the first 2/3 approximately of chapter 3 or module 3 that's in this, but it's just mostly about function notation. If you understand what function notation means, that's a lot of this. So go ahead and take a look at this. Like I said, you can do and redo the problems up through midnight tonight, so there's no danger like, oh my gosh, I just wanted to try this in class, but I didn't do it right. Doesn't matter, you can redo it later.